specific type of equilibrium expression that has to do with solubility. Okay, and it's just called KSP. So you're looking at, hey Michael, can you like put that away because the other two guys can't focus if you're doing that. So what we're going to look at here is a solubility product. All right, so what determines whether or not a solution is considered soluble or a substance is considered soluble or not? And it really depends all on KSP here. And something you want to think about is the term soluble and insoluble. All right, we'll refer to, even though we refer to substances as insoluble, that doesn't just that such a small amount of it dissolves that hardly any of it's going into solution. So we consider it insoluble. Okay, so you know, for example, there we got slightly soluble salts get to an equilibrium. Okay, in terms of cations and anions, essentially, you know, the concentration of the ions is what's truly important here, and calculating those concentrations is what's important as well. Because what you want to pay attention to here is, in terms of KSP, when we look at KSP down here, because you're looking at a solid that's dissolving into two aqueous ions, essentially. Okay, you have a solid and it goes into its ions. All right. Because you have a solid, right, the equilibrium expression here is only the products, is only those aqueous ions, the concentration of those ions there in solution. Okay, so there's nothing, it's all over 1. So we're only really concerned about the ions that go in solution. So if you have something like, you know, if we look at calcium fluoride there, and we write the KSP for this guy, you got the concentration of calcium times concentration of fluorine fluoride squared. Okay, so you still are treating it the same way. You just, there's no reactants to put in the equation now because it's a solid. Okay, and if we look at, in this case, they gave us the KSP as 4.0 times 10 to the 11th. We can figure out the molar solubility for each ion. Okay, because all we're going to do there is change that to, so KSP is going to be equal to X times X squared. I'm sorry, 2X squared. Yeah, that's correct. There we go. Okay, because your change is going to be X and 2X. And you just plug that into your expression. So ultimately we get X times 4X squared. Right, so that's going to be 4X cubed is going to be equal to 4.0 times 10 to the 11th. Okay, and you just ultimately you're solving for X. So here you're going to start getting some weird, you're going to have to start taking some cube roots and other, you know, larger roots essentially here to figure out what the molar solubility concentration of that ion is going to be at equilibrium. Okay, so in this case, X is going to be, we'll just crank that out real quick. And then cube root, so math, cube root, second answer. So X is equal to 2.15 times 10 to the negative 4. Okay. For example here, this would be the other type of problem here where if you had to solve for the KSP, so in this case, KSP is equal to the concentration of lead 2 plus times the concentration of chlorine squared, right? So remember our change for this reaction, right? Our change for the reaction, we got plus x and plus 2x. So when we plug that in, we have, and we know the change, they're telling us what the concentration is at equilibrium. Okay, so they're telling us it's 1.62 times 10 to the negative 2 times, and we got to take two times that amount in order to figure out what the chlorine concentration is. So 2 times 1.62 times 10 to the negative 2. So we get 0.0324 squared. And will give us the KSP. Okay. So a KSP of 5.184 times 10 to the minus 4. There we go. All right, not too difficult. They're all pretty straightforward. Okay. The one thing that you can, there's a couple more example problems there. The one thing that you can use KSP for is talk about, you can compare solubility of different substances to one another. Okay. So if we look at, I'll come back to these two problems in a second here if we can talk about this real quick. So if we can compare KSP values, we can decide whether or not a substance is more soluble or less soluble than another substance, okay, by looking at the equilibrium constant. So in this case, the key here, though, is the ion-to-ion ratio. You can only compare KSP values when it comes to the ion-to-ion ratio. So if they're the same, for example, in these first example, it's always just, it's a 1-to-1 ion ratio here for all of those substances. So we can directly look at the KSP and decide whether or not what's most soluble and what's least soluble. All right, the larger the KSP, the more soluble the substance is. So in this case, the most soluble substance is calcium sulfate, then it goes to copper iodide, and then silver iodide. Okay, you can look right at the KSP and decide which is more soluble and which is least soluble. Now, down here, the ion-to-ion ratio is not the same. All right, so this will cause us some issues. You've got to figure out, essentially, you need to find X. Larger the X, more soluble. Smaller the X, less soluble. Okay? Larger X, more soluble. And really, one of the easier ways to do that is you see that this bottom guy breaks up into 5 ions, so it's going to be more, it'll turn out to be more soluble than the other one. All right, we'll see you guys tomorrow. AP workday tomorrow.